There's yet another limitation or non-idealistic characteristic to operational amplifiers. Amplifiers have a maximum rate at which the output voltage can change, and this is known as the slew rate. The slew rate is defined as the maximum rate at which the output voltage can change. The slew rate limiting can be easily seen and measured by applying a step function to the input of a unity gain voltage follower amplifier. The output of the op-amp cannot change instantaneously, but it will change as quickly as it's able to. The output will look something like this, where the slope of that line, so the output is changing as quickly as it can, and the slope of that line is known as the slew rate. The slew rate is typically specified in volts per microsecond. The mechanism that limits the slew rate is beyond the scope of this class, but the general problem lies within the physical structure of transistors. It simply takes time for transistors to change from one state to another. They change very quickly, just not instantaneously. The amplifier will change its slew rate until it catches up with the input or until the input changes. Now, it's important to realize that the slew rate mechanism is different than the dominant pole low-pass filter characteristic of the op-amp that we've studied. The dominant pole is a single time constant RC circuit. When we apply a step function to the op-amp, we are actually producing the step response of the RC circuit. So the dominant pole or the low-pass filter characteristic occurs when we apply a step response or step input to the amplifier. And the single time constant aspect of it, the V out, will be of this form, where omega sub t is the unity gain bandwidth. Now, the maximum rate of this step response occurs at t equals 0 and is equal to the derivative of this with respect to time evaluated at t equals 0. So we have then dv dt at t equals 0 is equal to the derivative of that, which is v. Then you got the derivative of the exponential is negative omega t times a negative, so it'll be a positive omega sub t e to the minus omega sub t t evaluated at t equals 0, which is then just v omega sub t. This then is the maximum rate that this step response is changing. The step response will not be slew limited as long as this product here is less than the slew rate. Well, omega sub t, that's the unity gain bandwidth. That's a characteristic of the function, or of the op-amp. So this product will be less than the slew rate for voltages up to a certain voltage. And then for voltages beyond the voltage where V equals the slew rate divided by omega sub t. If the step input has a voltage greater than the slew rate divided, let's say this right. If the voltage is greater than the slew rate divided by the bandwidth, the unity gain bandwidth, then it's trying to change faster than the slew rate limitations of the amplifier will allow it. But as long as the voltage is less than this, the step response will not be slew rate limited, and it will take on that typical exponential formed step response. Data sheets will either specify a slew rate, and as I mentioned, it's typically specified in volts per microsecond, or as is the case in this data sheet for the LM324, it will give us a plot of this step input and the corresponding slew rate limited pulse response. So the slew rate then, under these circumstances, the slew rate is just equal to the change in voltage per change in time. Now, here it looks like we're going, what is it, 1, 2, I call it about 2.6 volts change. And the length of time that it takes to do that is from here to about there. So from 10, say, to 18 microseconds. The delta t would be 8 microseconds. and the slew rate then would be 0.325 volts per microsecond.